Kia ora to everybody in my physics class. As I record this, it's the 18th of March. Other physicists might be looking at this too, but maybe at a different time. I've just got to get my clicky thing going along here, and I might also get myself a pretend mouse laser pointer. This question comes from pages 114 and 115. Question 1 in the workbook, and the first bit looks like that. I've only included the bit from page 114. The rest of it's just words, and I can talk about them. We're asked to find the gravitational potential energy lost by the barrel as it rolls down. Well, mass is 5.7, height is 1.2, Earth's gravitational field 67.1 joules. The textbook gives us 67. I'm happy with that. That's a nice rounding on their part, and a good correlation for my part. The total kinetic energy will be that value because the gravitational potential energy lost becomes kinetic energy. And we have two types, so we need to consider that. We need to find the rotational velocity, and we can do that. Omega is V upon R, or V equals R omega, and rearrange. 4 divided by 0.27, and that's 14.8 in mine, and the book gives 15. That's cool, we're on track here. Linear kinetic energy is a half mv squared, half times 5.7 times 4 squared 16. Get 45.6, and the book gives me 46. Nice. Rotational kinetic energy is what's left over. 67.1 minus 45.6. I get 21.5, and the book says 22. We're on track. Now the rotational kinetic energy is EKR. Swap sides. EKR is a half I omega squared. Then multiply both sides by 2. I made a mistake there, sorry. Rotational kinetic energy is EKR. EKR is a half I omega squared. Swap sides, so and then multiply both sides by 2 to get rid of the half. Divide both sides by omega squared, and we've got I by itself. I is equal to 2 times 21.5, 43, divided by 14.8, and that's a smudge over 200. So 43 divided by a bit over 200 should be a bit less than 0.2, and that looks good to me, and the book gives me 0.2 kgs meters squared. Now, this is where it gets a bit conceptually weird. The circular speed of the edge of the barrel was assumed to be the same as the linear speed at which the barrel was traveling. This is a question from the book. Consider the point C in the diagram. It's on the outer edge of the barrel, and at the instant shown is in contact with the slope. The barrel has both rotational motion and translational motion. This means point C has two simultaneous velocities. Describe what they are and in which direction each one is acting. Alrighty, so I'm going to look at this. Point C has translational motion and rotational motion. The whole barrel is moving down the hill. And if I just duck back and check, top right to bottom left, my screen, top right to bottom left. So it's going to be going, the whole barrel is moving like this. At the same time, the barrel is also rotating anti-clockwise, like that. And so therefore the bottom of the barrel, which I will draw like this, there's the barrel. So we've got this velocity down here. That's the whole barrel, and I've replicated that at the bottom, because the top, bottom, middle, every single part of it's moving down the hill. At the same time as that, the barrel is rotating around this way. So every point will have an instantaneous tangential velocity. I'll repeat that. Every point will have an instantaneous tangential velocity. And the bottom has a tangential velocity going up, like that. And the two add together to make nothing, because the bottom of the barrel is touching the road. Now, this is kind of cool, because we can explain that, and I will do that very shortly, which is quite tricky actually, but we'll get there. The velocity of point C at that instant must be 0, because the barrel is touching the ground and not slipping. If the barrel is not slipping, then it must have the same linear velocity as the thing that it is touching, or the point of the barrel rather. The point of the barrel touching must have the same linear velocity as the thing that it is touching. The ground's not moving, has a velocity of 0, to the bottom of the barrel has a velocity of 0. And I'm going to finish what the book says here and then add my little bit onto it. The speed of the edge of the barrel must have the same speed as the barrel, because the bottom of the barrel has two velocities added together to make a total velocity at that point. This way, sorry, like that. One going this way, one going this way at the bottom, and they add up to make zilch. The total velocity of that point is 0, or it would be sliding. Spin speed must be the same as the linear speed for the barrel to remain in contact with the ground. The spin speed and linear speeds are opposite and add to 0. A good way to think about this, because that is what the book says, and I agree with it. There's something else we can add. Imagine we had a car being carried just above the ground on a low truck down a road at 100 km. So I'm thinking in my mind of the Ruhr car straights, but that doesn't matter. The vehicle has a speed of 100 kilometers per hour, which I'm going to call 28 meters per second because it's close enough. 28 meters per second. At the same time as that, the car, if we park the car up, park the carrier up, park the truck and the carrier up, and we started up the engine of the car and put it in gear, while the wheels were lifted off the ground, the drive wheels of the car will be spinning, and the bottom of the wheel will be spinning backwards. So we've got the bottom of the wheel spinning backwards, then we added onto the whole car moving forwards, and we finish up with the bottom of the wheel having two velocities, a tangential spin velocity back, and a carried or translational motion forwards. If we carried that car on the truck, or on whatever it is, with the wheel spinning in the air down the road, as we go past, we would see that the bottom of the wheel would have the same velocity as the ground, which is 0. It's got a backwards bits added onto frontwards bits. If we then drop the car onto the road at that point, it would just touch down and keep rolling. It wouldn't be the opposite of an aeroplane touching down, because when the aeroplanes touch down, their wheels skid because they're not turning. This is basically what's going on here. I hope that helps. If you're stuck, ping me an email and I'll do what I can to extend it, but I think that should cover it. Cheers, everybody.